Right, in this example, we're going to use the linear approximation to approximate the square root of numbers that are near 4. And so when you're using an approximation or a linear approximation, you center it around a value that you know you can evaluate quite easily. So we know how to take the square root of 4. But to take the square root of 4.005 by hand is not so easy. And so we're going to use a linear equation to do that. So we're going to start, and again, you want to use some scrap paper here and do some of the scratch work off to the side, and then we'll fill the table in. We've got our function. We've got f of x equals the square root of x. We're centering it at a equals 4, and we want to find the linearization. So in order to find a linearization, we want to find f of 4, which would be the square root of 4, or 2. We want to find f prime of x, which is 1 over 2 square roots of x. And we want to find f prime of 4, which would be 1 over 2 square roots of 4, or 1/4. So my linearization, remember it's f of a, in our case f of 4, plus f prime of 4 times x minus 4. So our linearization f of 4 is 2 plus 1/4 times x minus 4, all of x. So we'll put our linearization expression right here. 2 plus 1/4 x minus 4. And the function itself is the square root of x. It's to use the linearization to approximate the square root of 4, I would plug a 4 in for x. So if I go back to the scratch paper to find L of 4, it's 2 plus 1/4 times 4 minus 4, this is 0, so I would get 2. So the square root of 4, when I approximate it using the linearization, I get 2. And the actual value of the square root of 4 is 2. So here my error is 0. Alright, now let's evaluate the square root of 4.005, again using the linearization, and then we'll find the actual value on the calculator. So 4.005, so L of 4.005 is going to equal 2 plus 1/4 times x minus, so this would be 4.005 minus 4. So we would get 2 plus 1/4 times 0.005. Now we can use a calculator to do this arithmetic here. The arithmetic is not too bad if you didn't have a calculator, but to save time, let's plug this in our calculator. Quit out of that. So we have 2 plus 0.25 times 0.005. We get 2.00125. So let's put that value in here. This is our linearization at 4.005. So 2.00125 is what this linearization gives us as an approximation for the square root of 4.005. Now let's actually find the square root using our calculator of 4.005. Not too bad. All right, the value is pretty close. We've got 2.00124996. And that's all I can fit there. And if we we want to find the error, we would just subtract these two values. So at this point I can just subtract the 2.00125, and I'm just going to take the absolute value of that. So I'm going to have 6 zeros, the error. Right, so this is the approximate error. So, I mean, I find this fascinating that you can use a derivative to get, or a tangent line approximation, to approximate the square root of some irrational number, and you get an error that is minute. So now the 4.005 is close to 4. And so let's do the same thing for, why don't you pause the video at this point, all right? And why don't you find the linearization at 4.05 using the tangent line approximation here, or the linearization, and also find the square root of 4.05 in your calculator, and do the same with the square root of 5, and just compare your error. And then start the video once you get those values. All right, so plugging in both of the 4.05 and the 5 into our linearization. The linearization for 4.05, I got 2.0125, and for the actual value, or the actual square root of 4.05, I got 2.0124611. That's as many decimal places as my calculator would hold. So again, the difference between the actual value of the square root and the approximation of the square root is still pretty close. I mean, we're good out to 3 decimal places were accurate, and on the 4th we're only off by 1/10,000th. So the last one, when we do the square root of 5, we get, for the linearization, we get 2.25, and for the actual square root of 5, we get 2.36068. So you can see, as you get farther away from the point of tangency, your error is increasing. But I still think it's pretty cool that you can use a linear function to approximate a square root function, and you get really, really close values.